Welcome, we're going to be doing Physics 220, lab number 8, and this is E over m of the electron. So the equipment for this lab may require a little bit more explanation. So this is, what we have here is kind of simulating a cathode ray tube. And so what we have is if we come in here, there's a lot of just random equipment in here, but we can try to show you what it does. But basically this is what we call an electron gun. So we're applying a steep voltage that is accelerating electrons through here, just kind of like a stream of electrons, and it's going through this kind of tube here and then showing up on this oscilloscope here. And so this green dot is the electrons hitting the screen after being accelerated through this tube, right? And so what we can do now is on this tube inside of here there is two plates which we can apply a voltage to, which will create an electric field. And this electric field, if we turn it on, which I can adjust this is measuring in volts the magnitude of the electric field, up and down electric field, which is causing the beam to deflect. So, right, it's like capacitor plates. Some electrons are going through, it's going to be drawn to the positive charges and repelled by the negative charges. And so it's going to go up if we turn the voltage up, and it'll go down if we turn the voltage down to like a negative value. We're basically just flipping the plates, right? And so that's the voltage part. We also have these two coils here, which we're going to send current through, and the current is going to produce an electric field, right? That's going to go sideways through here. And then if we think about Lorentz law, right? If an electron is coming in here and it experiences some field, it's going to deflect one way or the other, right? And so we have a power supply powering the current through here, and what we can do is we can adjust the current. If we increase the current, it goes down. If we decrease it, it'll go back up. And so if we think about it, the increasing the current causes it to deflect downward. So if we think about the right-hand rule, right, the electrons are coming in, I don't know how to do this, coming in this way, right, they're experiencing either a deflection that way or a deflection this way. If we increase the current, it goes down, so that means that the magnetic field must be going this way. And so we have a magnetic field this way, electric field, let's see, down, right? No, up, because then we have negative to positive. Positive's up here, negative's down here. And so by adjusting these fields, we can vary how the electrons are shooting out onto the screen, and then by some ingenuity, we can find the charge to mass ratio of the electrons. All right, so to get started here, we're going to need to answer the first question here, which is where we want to express the charge to mass ratio in terms of the accelerating voltage of the electrons that's pushing the electrons out, right, as well as the velocity when it hits the screen. And so one thing we should recall from your introductory physics courses is that kinetic energy, just for any particle, is given by 1/2 times mass times velocity squared. And so we have that ratio, or that expression, and in this case, for any accelerating charge over a voltage, if it's starting at rest and then gets accelerated over the voltage, the kinetic energy as it leaves is going to be equal to the charge, which in this case is just E, times the voltage that it went over. And so this ratio, or this term, is going to equal 1/2 mv squared for the electron. So just use some simple algebra to find E over m, and then we can go ahead and continue on here. So the first thing we want to do is observe the location when everything is off. So I've turned the current off, so nothing's going, there's no magnetic field, and I've set the voltage, the deflecting voltage, to be 0. And so we'll notice that the beam here is, we don't care about where it is left and right, because we're only going to be deflecting it up and down, but we're negative about 1.5 on the y-axis. So we'll see these little slots. We're halfway between the -1 and the -2. So that's important because what we're going to do now is we're going to turn this on, and we're going to go ahead and deflect the beam. So you should have recalled, right, if we turn up the voltage, let's see if I'm doing this right. Yep. Turn up the voltage, it deflects it upwards. So I turn it up to like 25 volts, doesn't matter. We just want to know the ratio, so I can pick any ratio. And then I'm going to increase the current until it goes back down, right? So increasing the current puts it back down. I'm going to adjust the current until it is back where it started. Okay, we're back to about negative 1.5 there. And so this is the current that is right now pushing the beam, well, the current that is causing the magnetic field to push the beam down. That's the voltage of the electric field, which is pushing the beam up. And those are in equilibrium. We're back to where we started. So there's no deflection, just going straight through. And it's actually all the data that you need, just some algebra and computations from here. Again, we're measuring voltage and current, but we want to know E field and B field, right? And so we give you some of these conversion factors or effective magnetic fields where, we take this current and we multiply it by this number and we get the B field. Take the electric field or the voltage, multiply it by this number, and we get the electric field of the deflection. And so once you have these two properties, we just recall that the forces from the two fields have to be equal because it's not deflecting, right? So we're setting these two forces equal to each other. That's what the forces are, right? E times E, E times the velocity times B. And so set those equal to each other. And then we'll apply the same ratio that we found up here in number 1 to solve for these quantities. And then for the expected, just look it up online, or I think it's in your packet as well. And these should be pretty close, hopefully. So that's it. That's the experiment that made J.J. Thomson famous, basically. And that's it for the lab. So hope you enjoyed it.